So I previewed this yesterday. I mentioned entropy. Entropy is this thing that really is like a measure of disorder, or I kind of like this definition, a measure of the dispersal of matter and energy. So it's a measure of how dispersed or spread out things are. We symbolize entropy with the letter S because, of course, the third and fourth letters of entropy are T and R, and what comes between T and R in the alphabet? S. And we always symbolize things by whatever letter comes between the third and fourth letters of them. So entropy stands for, S stands for entropy, of course. I don't know where S came from. Maybe it came from second law or something like that. But the idea is everything that happens in the universe is constantly making the universe more disordered. This is the second law of thermodynamics. Everything makes the universe more disordered. Kind of a crazy concept. So today we're going to try and see how that applies to chemical reactions. And I got to say, those of you who are watching at home, you can't smell the overpowering smell of like 30 lollipops being consumed at once. But there's this sickening sweetness to the air in the room right now. So happy Valentine's Day. All right, so I want you to think for a moment at your table. You can talk to each other. When will entropy be higher? So you want to take this idea and think about when you have number of particles. Someone shouted out tomorrow, which is actually a good response, because tomorrow entropy will be greater than today, because entropy is always increasing. But no, if we're comparing two situations, one with more particles and one with fewer particles, which one would have higher entropy? And if we're comparing states of matter, one where there's a liquid and one where there's a gas, which has more entropy? If we're comparing two situations where the temperature is lower versus higher, which has more entropy? And then these last two, volume and pressure. I'll kind of take the pressure off the board, because really pressure and volume just go in opposite directions. So whatever you say for volume would be the opposite. But if we're comparing, one collection of particles in a small container and the same collection of particles in a big container, which would have more entropy? So I want you to make decisions on those four things. Take a minute to make a decision for yourself. All right, number of particles. So, Jack, what did you guys say? Greater number of particles or fewer particles have more entropy? More particles, more entropy. All right. If you have more particles, there's more different ways they can be arranged. There's going to be more random motion, more ways things can bump into each other. So, greater entropy. All right, how about state of matter? What state of matter is going to have the greatest entropy? What's going to have the least? Rip? Yeah, gas will have the greatest, liquid will be in the middle, and then solid, the least entropy. I mean, it turns out I actually should space them differently. Like, there should be a big gap between gas and then liquid and solid, because gas is way more spread out, way more entropy. Liquid and solid are much closer together. All right, temperature. High temperature, greater entropy. Yeah, high temperature. Particles are moving around more quickly. And also, I'll refer back to this Maxwell-Boltzmann distribution from the beginning of the year. You may or may not remember it, but it was a graph of the speed of particles versus the number of particles in a collection that would move at that speed. And we talked about how that distribution changes at low versus high temperature. So at low temperature, particles were kind of bunched up around the low speeds, and maybe there was a tail of a few that had high speeds. Oops. But then at higher temperature, that distribution kind of spread out more. And so there was a wider distribution of kinetic energies for the particles. And this is one thing in the new AP Chem curriculum. This is how they describe why higher temperature has greater entropy, because there's a greater dispersal of energy throughout all the particles. And then last one, volume. So if you have a collection of particles in a container, check. Would that be greater entropy at high volume or low volume? In which cases are the particles more dispersed? High volume, yeah. High volume, so bigger volume, more entropy, smaller volume, less entropy. All right, so you want to conceptually have this idea that we can compare different situations as to how much entropy they have. We then want to take those ideas and apply them specifically to chemical and physical processes. So we want to apply them to phase changes, apply them to chemical reactions, and think about, for a given chemical reaction, whether it causes an increase in entropy of that system or a decrease in entropy of that system. Someone in the last class asked a good question. Well, how can you have something that decreases the entropy of the system? Didn't we say the entropy of the universe has to increase? Always. And the answer is yes, it does, but that's the entropy of the whole universe. You can have the entropy of one part of the universe become less. So you can have processes where delta S is a negative number. It just means the surroundings are going to have to compensate by having even greater entropy. So we'll talk more about that in a minute. But I want you to just look at each of these processes and think about whether delta S would be a positive number or a negative number. Does each of these increase the entropies of the particles involved or decrease the entropy of the particles involved? Go ahead. Okay, what did we decide? First reaction here, or actually not a reaction, a phase change. Positive entropy change. We start with solid, less entropy. We end up with more entropy because it's a gas. Second one? Oh, question about the first one. So the question is, what direction am I referring to? We're always talking about the left to right direction. Whenever I talk about a reaction and say delta S, I'm talking, or delta H or delta G, we'll see a little later, I'm always talking about from the left to right direction. If I flip the reaction over, the sign just flips on those delta values. Yep, so always from left to right. All right, second reaction. Look, said delta S is negative. Why? You have a solid and a gas. Again, the gas has more entropy. The solid has less. You're taking these particles that are spread out, and now you're putting them together. All right. Check. Does bonding two things together in itself lower the entropy? Usually. Yeah. All right, and then third, this last reaction here. Positive. Why'd you say positive? Yeah, so over here we have 6 gas particles. And over here we have 7 gas particles. So greater entropy on the right. Any questions about that? So you should be able to look at most processes and determine whether delta S is going to be positive or negative. If there's no change in the number of gas particles, you probably can't tell. Okay, but if there is a clear change, usually you can tell whether delta S would be positive or negative. All right, I'm going to take a break for a moment. Okay, so we have a conceptual way to find delta S, or at least find the sign of delta S, if we want a numerical value to go with it. Essentially, what we need to do is we need to know the entropy of the products and the entropy of the reactants. Just like we said yesterday for delta H, you could take the sum of the heats of formation of the products and the heats of formation of the reactants and subtract and find the change in enthalpy. You can do the same thing with entropy. If you look at your formula sheet, you'll see this same equation right above the one for delta H. Okay. Now the thing is, how do we know how much entropy stuff has? How do we know those values? Well, turns out we have this theoretical law, the third law of thermodynamics, which basically says the entropy of a perfect crystal at 0 Kelvin, so any pure substance, make a perfect crystal of it at 0 Kelvin, and it has 0 entropy. And then if you warm it up, and it undergoes phase changes and such, there's a certain increase in entropy for each of those things. And someone with much more experience with thermodynamics than us can figure out how much change in entropy there is and can find an actual entropy value for everything. And so at standard conditions, they've listed the entropy values for lots of different substances. So these S0 values you can look up. And so just like for delta H, you can just look those up in your book, other sources, and you can find delta S. So if you ever need a numerical value for delta S for a reaction, one way to find it is to look at the reactants, look at the products, find the entropy values for the products, subtract the entropy values for the reactants. Okay? So this is also on your formula sheet. All right. So now let's put, oh, question. Oh, great question. I was just about to say, why do we care about entropy? What does it tell us? Okay? And so what entropy is really going to tell us is whether a reaction is going to happen or not, or whether a reaction wants to happen or not. So for a long time, there's been this word that we use to describe reactions that want to go in the forward direction in order to reach equilibrium. We call them spontaneous. It's a little different than the way you would use spontaneous in your everyday life. The good news is the AP test seems to be moving away from the use of the word spontaneous. But when you take a college class, I'll bet your professor's still going to use the word spontaneous. So I'm going to use that, but I'm also going to intersperse it with the language that they're kind of switching to for AP. A spontaneous process, also known as a thermodynamically favorable process. It's a reaction that would occur in the forward direction in order to reach equilibrium. So it would move in the forward direction without an external input of energy. In order to reach equilibrium. So these are processes that generally you think of as happening on their own. You don't have to force them to happen. So what's something that would happen on its own that you don't have to force to happen? Any ideas? Sure, if you add sodium to water. Reaction between sodium and water is something that's spontaneous. It's more of an obscure example. I'm thinking more of kind of things you'd run across in everyday life. But that works. What about what happens if you put salt in water? It dissolves on its own. Right? That's a spontaneous process. What do you think of others? So evaporation of water wouldn't be necessarily considered spontaneous unless you're talking about if there's a low vapor, if there's a low pressure of water vapor above it. So I suppose it is spontaneous under certain conditions, but not always. All right, reaction between acids and some solids, sure. I do want to draw a distinction, though. Spontaneity, or saying something's thermodynamically favorable, it does not imply that the reaction will happen quickly. Okay? So it does not imply that the reaction will occur at an observable rate. In other words, there are lots of reactions that technically are spontaneous or thermodynamically favorable that they just don't happen on their own because the activation energy is too high. Question? So rusting is spontaneous, yeah. And that occurs slowly. Big example would be there's lots of things in this room that are flammable. And yet, they're not currently on fire. So the burning of all the paper in this room or all the wood in this room, those are spontaneous reactions or thermodynamically favorable reactions. But they have very high activation energies. And so they're not happening at room temperature. Not because they're not thermodynamically favorable, but because the activation energy is too high. Question? So no external input of energy. They would move in the forward direction without an external input of energy in order to reach equilibrium. So right now, there's oxygen in the room, and there's flammable stuff in the room. Those reactants are not at equilibrium with their products. And they're not going to reach equilibrium unless the room burns, because the activation energy is very high. So when we talk about spontaneity, we're not talking about activation energy. We're just talking about the difference between the reactants and the products. So if they had enough activation energy, would the equilibrium favor the products or the reactants? That's what thermodynamics tells us. So combustion is thermodynamically favorable. But doesn't happen usually at room temperature. So this is kind of an important thing to us because we couldn't really exist. If everything just constantly went to equilibrium, we really couldn't exist because certainly most of the, all the carbon in our body would thermodynamically prefer to be carbon dioxide rather than being all the different things that make us. So this is an important point. Spontaneity, when we say something spontaneous, doesn't mean it's actually going to happen at a given temperature because activation energy may prevent that. Another example is, this is a relevant Valentine's Day example. Diamond turning to graphite. Is technically, it's thermodynamically favorable, so it's actually a spontaneous reaction, but very slow. But if diamond were allowed to reach equilibrium with graphite, most of the diamond would turn into graphite. Well, they're the same atoms, they're just bonded differently. All right, so the question is, how would they do that? Well, that's the point. There's not a real viable mechanism to turn diamond into graphite because you have to break lots and lots of bonds and then reform new bonds. But the breaking of those, all those carbon-carbon single bonds requires a huge activation energy. And so it's very slow. But technically, it would be considered a spontaneous reaction. All right, so we care about entropy because entropy really tells us if things are going to be spontaneous. A process can only be spontaneous if it follows the second law. And what does the second law of thermodynamics say? It has to increase the entropy of the universe. Bless you. So a process can only be spontaneous if it increases the entropy of the universe. What that means is if a process produces order in one place, if a process makes the atoms and molecules in the system more ordered or less disordered, it has to increase the entropy of the surroundings in order to be thermodynamically favorable. Yep. Right, so the question is, just because the delta S for a system, for a given process is negative, doesn't mean it can't be spontaneous. It can be spontaneous, but there needs to be this offsetting increase in the entropy of the surroundings. So how would you increase the entropy of the surroundings? What do you think the mechanism for that is? You can release heat. So a process that increases the order of the system will often also release heat to the surroundings. And when you release heat to the surroundings, temperature of the surroundings goes up. When you increase the temperature of the surroundings, the disorder of the surroundings increases. How many people argue with their parents about cleaning their room? Anyone? All right. So here's your argument next time. You say, look, if I increase the order in my room, if I decrease entropy in my room, I have to increase the entropy of the rest of the universe by an even greater amount to offset it. And really, like, is that worth the price? I can't promise that they'll buy it. But if you clean your room, how is it that you're making the surroundings more entropic? When you clean your room, what are you doing that's increasing the entropy of the surroundings? Well, you're making space, but there's something else. Anytime you move around, what are you doing? You're burning carbohydrates in your body and essentially releasing heat as you do it. And when you release heat, again, it increases the entropy of the surroundings. So there's this balance between heat and entropy. This balance between the enthalpy of a reaction and the entropy of a reaction. Okay? When you increase the order, that's decreasing entropy. So entropy is like disorder. So if you want to make something that's more ordered, where things are arranged in a more specific way. Where there's only a couple of possible outcomes. So like in the cleaning your room example, right? There's more entropy if your stuff is just scattered everywhere, right? Because it's just kind of in random locations. When you clean, you actually put them all where they belong, into an ordered arrangement. You know, that is analogous to, say, taking small molecules and building larger molecules that have a more specific structure. Okay? When you take small molecules and build larger molecules with a more specific structure, you're increasing the amount of order, or the other way to say that is decreasing the amount of disorder. All right, so the question is, does this mean that generally exothermic reactions tend to be spontaneous? Great. All right, I'm going to skip this. This is just, because I want to get to your question. This is just saying if you shake a box of checkers, they're not going to like suddenly rearrange themselves back into the set arrangement for the board. It's just, you know, entropy doesn't spontaneously decrease. It always increases. So to get to Maria's question about enthalpy, yes, enthalpy is one thing. A decrease in enthalpy is one thing that can make a reaction spontaneous. Now, to put these two together, we actually tie them in a concept we call Gibbs free energy. So Gibbs free energy, which is G, is basically this value that puts together enthalpy and entropy into one value that'll tell us if a reaction is going to be spontaneous. Okay? It'll tell us whether the reaction, whether the second law says the reaction should go forward or backward. Delta G is constructed by putting delta H for the reaction together with delta S as delta H minus T delta S. Okay? So let's think about this. Well, hold on. Next thing that's really important to know is delta G, for a reaction to be spontaneous, delta G has to be negative. So if delta G is negative, the products are more thermodynamically favorable than the reactants, and the reaction will proceed in the forward direction toward equilibrium. So for a reaction to be spontaneous, we want delta G to be negative. If we want delta G to be negative, then what's the preferred value for delta H, positive or negative? Negative. And what's the preferred value for delta S? Positive, because this is minus T delta S. So if delta S is positive, then this term becomes negative. Okay? So T is temperature. Yep. So basically what that says is the change in entropy becomes more and more important as the temperature increases. I really like the way that the AP course description framed this. No, I really liked it. That's why I put it in here. So this is Enduring Understanding 5.E. Right? If you look through the front of your notes, I've put all the enduring understandings and everything in there, and I encourage you to read those, because a lot of times it gives you insight into the way they phrase things and the things that they're going to emphasize on the test. But it says, chemical or physical processes are driven by a decrease in enthalpy, so a negative delta H, that's one thing that can make a reaction spontaneous, or an increase in entropy, so a positive delta S, that's another thing that can make a reaction spontaneous, or both. So for a reaction to be spontaneous, you need either negative delta H, and you need that negative delta H to be bigger than the delta S term, or a positive delta S, and you need that term to be bigger than the delta H term to kind of win the day, or both. If you have both a decrease in enthalpy and an increase in entropy, that's like the double whammy. Those are the processes that are really thermodynamically favorable. Okay? I'm glad you said, the audience just said, that's really cool. They said it in unison, in fact. But I think it's a really cool idea, and it allows you to think about everything that happens around you in terms of, okay, is this happening because it's releasing heat, or is this happening because it increases its order, or does it do both? So now I have just a couple of repetitive slides because I want to hammer this point home. Because every year I get a couple of students who, like, during week 2 or 3 when we've been studying thermodynamics, they're like, wait a minute, what does it mean when delta G is negative? You need to know that. This is an important one. So if delta G is positive, what that means is the products are less favorable than the reactants. It means that the reaction would like to proceed to the left. And in terms of we would say the reaction is not spontaneous. Or the other way to say that is thermodynamically unfavorable. Let's see, thermodynamically, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17-letter word, just like electronegativity. Wow. So you can see why textbooks have tended to use the word spontaneous. But I do think thermodynamically unfavorable is a better descriptive term than spontaneous. So I'm giving you the term spontaneous just because it's in all the textbooks, and it's probably going to be the language that your college professors use. Really, it's thermodynamically unfavorable. If delta G is negative, we can say all the reverse. Okay, so the products are more favorable than the reactants. The reaction will go to the right. And we could say it is spontaneous or thermodynamically favorable. What questions do you have about the meaning of delta G? Mark? So the question is, delta G is basically how good the reaction is for the universe. Maybe, I wouldn't say how good it is for the universe, but maybe it's a measure of how much the universe wants the reaction to happen. If there's a big negative delta G, then the universe is like, yeah, go, reaction, go. If there's a big positive delta G, the universe is like, go in the other direction, reaction, go in the other direction. So we think of it as a driving force that's like pushing the reaction one way or the other. Yeah. But again, the reaction may not be able to go in the direction it, quote, wants to go in, because this does not consider activation energy. So there's always that activation energy consideration that might prevent it from going. So we often contrast the thermodynamic side of the reaction, whether the reaction wants to go forward or reverse, and then the kinetic side, whether it has enough activation energy to actually proceed in either direction. So the question is this how I would recommend you think about this? There's actually several slides throughout the remainder of the lecture slides where we're going to talk about interpreting delta G in different ways. And so one way to interpret it is as that driving force of whether the reaction wants to go forward or reverse. I like to think of the delta H side of things. Delta H is telling us about the potential energy of all the attractions and repulsions. Delta S is telling us about the disorder. And then delta G is telling us, all right, when I combine both of those factors, which way does the reaction want to go? I have another slide just to summarize again. If delta G is negative, the reaction wants to go forward. And if delta G is positive, the reaction wants to go backward. And again, there's nothing new on that slide. I'm just repeating it because I think repetition sometimes helps, because this is a really important idea. All right, so we'll kind of close by thinking about delta G in a certain way. A lot of times, delta G is described as a measure of the usable energy from reaction, or how much useful work the reaction can do for you. So from this perspective, you're thinking about delta G as a measure of useful energy that a reaction can give you. Here's the way I would interpret it in that context. Delta H, we said, is the change in potential energy of the particles. So delta H tells you, well, how much does the potential energy of the atoms and molecules change during this process because of the fact that they're attracted to each other, repelled by each other? Delta S, remember, is how much their disorder changes. So how much change in disorder there is. So then this minus T delta S term can be thought of as the cost of entropy, the cost of disorder. Delta H tells you how much potential energy change you have. So a given reaction may give off a bunch of energy. There may be a big decrease in potential energy. But if the reaction also brings more order to the atoms and molecules, you got to pay for that. Some of the energy has to go into creating that order. And so the net amount of usable energy you get out is going to be the amount of potential energy change with this chunk taken out that you had to pay to make things more ordered. All right? So from this perspective, the minus T delta S term is really the total cost of making things more ordered. The question is, when I say usable, do I mean to the environment? I mean usable, and this is again kind of a squishy definition I'm going to say, but usable to do the work you want it to do. So for instance, in biology, delta G comes up a bunch in AP Bio, I believe. Am I correct in that? Yeah. You talk in terms of delta G because delta G tells you how much useful energy to the organism that the organism can use to keep itself alive for its own processes. That's what delta G is. Delta H is not as important because that's maybe the total change in potential energy, but you need to account for this cost of ordering things. Okay? So the T delta S term is the total cost of arranging atoms and molecules in a specific way. So entropy tends to take its toll when you want to use a certain amount of energy. You want to use a reaction that gives off X amount of heat. Some of that is going to be lost. And that's one way to think about delta G. When we come back in a couple of weeks, we will look at examples of this and apply this to individual examples. And we will give some different interpretations of delta G as well. Because delta G is this crazy concept, and I like the fact that you can think of it from different angles.